In this video, we are going to learn how to use the law of conservation of energy to solve problems like this. Here you have a mother pulls her daughter whose mass is 20 kilograms and who is sitting on a swing with ropes of length 3.50 meter. Backward until the rope make an angle of 35 degrees with respect to the vertical. She then releases her daughter from rest. What is the speed of the daughter when the rope makes an angle of 15 degrees with respect to the vertical? So let us first sketch the problem. Let this be the initial position of the swing. So I'm going to draw the rope and let this be the swing. The length of the rope we will take as L, which is 3.5 meter. And let this be the reference point of the swing. Now reference point is like the starting point. And at the reference point, we take the height of the object, the height at which the object is at, to be 0. Now when the mother pulls the swing back, let the second position of the swing be here. And this is at an angle of 35 degrees with the vertical. The length of the rope still remains L. And let the swing be raised to a height h1 from the reference point. So if the total length of the rope is L and h1 is the height at which the swing is raised, the rest of the distance from the suspension point, we can write it as d1. So if we write a relationship between h1L and d1, we get h1 to be equal to L minus d1. Now when the swing is released, we need to find the velocity of the swing at a second point, which is at an angle of 15 degrees with the vertical. So at a point like this over here. Let the height at which this point is raised to be h2. Let this be h2. And just like we wrote for h1, I can find h2 as L minus d2, where d2 is the rest of the length here. If I want to find what is velocity at the second point, let this be my first point and let this be the second point. If I want to find what is the velocity of the swing at the second point, I have to use the law of conservation of energy. Now, law of conservation of energy says that energy of an isolated system remains constant. That means if I take any 2 points, total energy of this 2 points has to be equal. So total energy at point 1 must be equal to total energy at point 2. Now total mechanical energy for any system is the sum of its potential plus kinetic energy. So if I'm finding total energy here, I have to do sum of kinetic plus potential. So I'm going to write total energy at point 1 as sum of kinetic energy at point 1 plus potential energy at 1, which is equal to kinetic energy at 2 plus potential energy at 2. Now point 1 is the highest point of motion for the swing. This is the point from where the swing will return. So velocity of the swing at this point is 0. That means velocity of daughter at this point will also be 0. So this point over here has only potential energy as its total energy, and there is no kinetic energy here. So kinetic energy at point 1 will be 0, and I just write here as potential energy, PE1. The second point, on the other hand, is in between. It's like It's between the lowest and the highest point. So it will have both kinetic as well as potential energy. Now let's substitute for their rules. We know that potential energy is given as mgh. So since it is for point 1, I'm going to write it as mgh1. Kinetic energy is half mv squared. This is for point 2. And potential energy at point 2 will be mgh2. Mass of the system is the same, so we can cancel off the mass. And when I cancel off the mass, I can rewrite this expression as gh1 equals v2 squared by 2 plus gh2. Now I need to find velocity or the speed, so I must rearrange the terms to isolate v. So I will move this gh2 to the other side, and since it is plus here, when I move it to the other side, it will become minus. So we write this expression as gh1 minus gh2 equals v2 squared by 2. Multiply by 2 and rearrange again, we get v2 squared equals 2g h1 minus h2. I took g common because it's with both the terms. Now take the square root to find the expression for velocity. So it becomes square root 2g h1 minus h2. So if I can find what is h1 and h2, I can find what is the speed of the daughter at point 2. We already know how to find h1, h2. We can just subtract the distance d1 from the length. But what is d1 and what is d2? How do we find that? So we have to use trigonometry here to find the length d1. If I make a small sketch of the region over here, we can show that this is how the diagram looks like if I make a sketch of that point. This is the length of the rope, this is d1, and this is the angle theta 1. So we can say theta 1 is 35 and theta 2 is 15 degrees. I can find theta 1 by using trigonometry. Since d1 is next to theta, which is the adjacent side, we will use cosine theta. We know that cosine theta is adjacent side over hypotenuse. So I get cosine theta 1 as d1 over L. So when we rearrange the terms, we get d1 equals L cosine theta 1. Similarly, we can get d2 as L cosine theta 2. So when we substitute this value over here, we get h1 as L minus L cosine theta 1 and h2 will be L minus L cosine theta 2. After getting the values of h1 and h2, I can substitute them in my final expression for velocity. So let's do that. I get v2 equals square root 2g. h1 is L minus L cosine theta 1 minus h2 is L minus L cosine theta 2. Now you can cancel off the terms which are common here. So if I open the bracket, I get 2g L minus L cosine theta 1 minus L plus L cosine theta 2. When I open the bracket here, this will become minus L, minus and minus will become plus here. So we can cancel off the L because it's L minus L. And when we solve for this, we get the final expression for V2 as square root 2g L cosine theta 2 minus L cosine theta 1. We can take L as common, 2gl cosine theta 2 minus cosine theta 1. Now you can substitute the values. So G is 9.81, L is 3.50. Then you can put cosine theta 2 is 15 and theta 1 is 31. And when you substitute this value, you get the answer for velocity as 3.17 meter per second.